You know, it's funny, whenever you come to a conference, you come prepared to put a presentation together, and you're all set to say exactly what you want to say. And it usually happens 2 weeks ahead of time, all right, because you have to deliver the presentations ahead of time so you don't get yelled at. And then you listen to everyone, and you think about what's going to happen in the conversations, and how are we going to progress from here. And I think that's where I've landed today. So the first thing I wanted to land on is the question of, really the question that was posed to us at the beginning of the seminar, and what was delivered out to the guests and speakers is Poland really this SMR technology incubator in Europe? Is it? Well, the answer is a resounding yes. Poland is so far out in front of many of the other countries, regardless of what the other countries are saying or doing. As you can see from, I would say, my colleague from OSGE, the progress is impressive. The capability of the country's supply chain and your technical capability and actually the regulator's capability is so impressive and so far along that you can't really say no to this question. You can't say maybe. The absolute answer is yes. So let me talk a little bit about NuScale and the work we've been doing in Poland, and I'll try not to refute too much of what I heard from my colleagues from OSGE. As you know, we have a friendly competition between GEH and the BWX300 and NuScale's technology, the NuScale Power module, and the Voyager plant configurations. It's usually not the right thing to do to talk about your competition, but we find ourselves always doing the same thing. I won't mention Westinghouse at the moment as they're progressing with the AP1000, which is their large-scale unit, but they did announce an SMR, which is going to come into the market very soon, and we'll pay attention to that and see how they progress. A little bit about NuScale. Many of you have seen this slide before. If you know me, you've seen it, you think, except for one thing: things keep progressing. All right, number one thing is the investment in NuScale and the investment in the technology keeps growing, we keep evolving, we keep moving forward. The bottom line is, on this slide, the information here is, this is what it takes to bring a technology, an SMR technology forward that is smarter, safer, cleaner, and cost-effective. So the $1.6 billion development costs, and it's development and licensing to be able to prove that you've done the right things with a qualified regulator, and we've done that. I did see that my friend Rob Rudich from the DOE had to leave early, but I did want to thank the DOE directly for their support for SMR's technology advancement and their continued support to see it through and to get the first project implemented in North America. And that is the carbon-free power project for the UAMPS company on the site of the Idaho National Lab. I do want to be clear, that is not a demonstration unit, that is a commercial unit, which requires approval by the US NRC, which we're in the process of gaining now. So you get the technology approved and you get the plant approved for operation. And that's the process we're in. Very quickly, and I do have a number of slides here that I don't want to bore you with because it's never a good idea to be between a hungry crowd and lunch. So I do want to present that there are a number of slides here that are really meant for context for when you're looking back and you're thinking about the things I've said and you have the presentation in front of you. It's just context. I won't spend too much time on each one. The bottom line is, on this slide, I realize I'm saying bottom line, the key takeaway is NuScale started in 2007. So we're not brand new. And we've advanced to the point of bringing forward our product, and we're beginning manufacturing. We're literally pouring the steel components now in Korea, and we'll be able to deliver those in early 2027. The first and only technology licensed, SMR technology licensed and approved by the US NRC. This is a picture I've been waiting for a year. This is the steel, and these are the components being poured for the NuScale Power module at Doosan Enerbility in South Korea. They will be able to be delivered on site, I think in mid-2027 for implementation, which would really put the carbon-free power project on a plan to be commercial sooner than 2029, but their project schedule is to be able to deliver energy to the grid for 2029 according to their power purchase agreement. And this is when you get trapped into a certain schedule paradigm between a technology provider and an actual customer is, what can you deliver, but when do they need it? Usually, the problem is you can't deliver fast enough and they need it sooner. That's not quite where we are. NuScale is able to deliver components, actual operational components in 2027, but the power purchase agreements don't begin for UAMP's carbon-free power project until 2029. So that's where we get into this discussion. Can NuScale deliver early? The answer is yes, but you gotta have a place to put a reactor, right? You have to have a reactor building, you have to have a plant in order to be able to deliver, and that will be available in late 2028 to put energy on the grid in 2029. We are ahead of all the competition. First and only technology licensed and approved. I've mentioned that. I'll keep mentioning that till anybody catches up. That's the bottom line. All right, I see a couple of smiles, thank you. That is the important factor. You don't have a technology until it's approved by a qualified and experienced regulator. We're going through that with KGHM support and delivering an application for general opinion. We're working with PAA on that. We're working with PAA and the NRC, bringing all the information together so that PAA will be well positioned to assess the technology for an operational license at the right time. A couple of items I will touch on as we go forward. As I'm sliding down here, I've talked about manufacturing a little bit. The coping period, that's an important factor for any any nuclear technology, is in the unlikely event that something should happen, how much time do you have in order to support the critical cooling of the reactor to ensure no significant damage occurs? A NuScale reactor, each NuScale power module being so small and the core so small, the coping period is indefinite. You don't need to do anything, and it will cool itself over a period of time. And I've got a slide to show you on that. And the unparalleled operational capabilities, I'll also touch on that in a moment. To really position yourself to be successful in plant implementation, you've got to have a 3D model, and you have to have your standard plant design done. You have to get the reactor, all your safety components, all your safety systems developed, evaluated, and designed. We've done it. The Voyager 6, which Rob Rudich mentioned this morning, is the first implementation. That's the first design that we're going to implement for the carbon-free power project. That is completely designed and ready to implement in Idaho. That's important to know. We have a plant parameter envelope that says this design can be implemented in a number of scenarios, in a number of situations, in a number of sites. It's ready, and it's proven. Just for a quick reference, I want to give you a view of the NuScale Power module and to show you its size, the fact that we've taken into account all the components. And I think the number one thing to take off of this slide is the ability to ship to site assembled. There is no on-site manufacturing of a NuScale Power module. If the site happens to be located in a difficult to get to position, we can disassemble it and deliver it like in 4 major components and then really just bolt it together at the site. So that's a difference between assembly and manufacturing. There's no welding to be done. Well, other than, the flanges, once you get inside the reactor building, you flange those up, etc. But the reactor itself, there's no major manufacturing to be done on site. It comes from the factory complete. I think the reason why I wanted to include this slide is it's a better image, and also the very last bullet. The NuScale plant is designed to have multiple modules in sequence, so it's kind of in an array. And you can build that facility to house any number of NuScale Power modules, and you can add them incrementally as you need to. That can also lend to, let's make a little bit bigger reactor building and start with, say, 300 megawatts to 600 megawatts sized number of reactors, and then add more as time goes on. And all it costs is the addition of the reactor and the associated power conversion equipment, steam turbine and the generator, et cetera. That can be very economical. I've heard a lot of talk about proven technology. NuScale's design is a pressurized water reactor, and it's based upon proven technology, which I think we got, what, 350, yeah, greater than 350 commercial operational PWRs around the world. I can't count the number that have been used in U.S. Navy and in nuclear subs and also in nuclear aircraft carriers, et cetera. The number is pretty significant. Can't really talk about that number. But the reality is we've taken that technology, we knew it was proven, we could see where the industry was going, and we decided to really kind of make it smaller, more accessible, and really the key was to make it so that the units could be delivered as assembled from the factory. Everything's factory built, repeatability, high quality, et cetera. Just for scale, the size of the NuScale Power Module is aligned to about the size of a steam generator of a large PWR. I put this slide in here for two different reasons. One was to touch on the size of the overall plant, which is about 14.5 hectares for a Voyager 12 configuration. That's 924 megawatts on about 14.5 hectares. That's pretty sizable. And the other element was to denote the three key elements of our triple crown of safety, which are no operator or control system action, no AC/DC power, and no additional water required for any kind of an event. The last bullet there, the last item, is the emergency planning zone ends at the site boundary. I'll come back to that in a moment. Important to note, it's not always intuitively obvious. We all talk about SMRs, and we're all thinking, you know, an SMR from one site and one plant to the next is going to be identical. Most of them really aren't, because what's going to happen is they're a little bit bigger, and you have to do a large number of manufacturing beyond assembly. It's manufacturing, and it's a lot of key effort on site. NuScale Power Module, you don't. So they come out of the factory. So if you built a 300 megawatt NuScale facility, a Voyager 4, in one area of Poland, and a Voyager 12 in the other area of Poland, those reactors are identical. They come from the factory the same. So the same people that operate and work on the Voyager 4 can work on the Voyager 12, can work on the Voyager 6, et cetera. The same parts. That makes for economical planning for maintenance and operation and support across the country and across the region. It's just not always intuitively obvious. This is the slide I wanted to talk about where we talk about emergency planning zone. You'll note that little tiny dot in the center is the emergency planning zone for a NuScale power plant, and that was developed for a Voyager 12. It's the site boundary. And it's the site boundary based upon that 14.5 hectare model. We didn't make the site bigger to incorporate the emergency planning zone. We matched the emergency planning zone for the small reactor. And the question is, so how do you get there? Well, the core, being so small, actually lends to that. So that's something that really needs to be considered. It allows for close proximity to points of use. So, district heating, you can put the plant right next to the heating circuit or integrated into the heating circuit. For working with a steel plant, it could be right next door. Does it need to be aligned with supporting a small community for electricity, for heat, et cetera? You can place the unit really as close as the constituents would allow it to be. I mentioned coping period. This slide is just to indicate that. The core is small. The design is such that you will water cool it until the water is, honestly, if anything happens and there is no more water, it'll air cool. One key thing I don't think that's always understood about NuScale's technology, the whole goal was to design the plant such that you could really provide enough energy to support multiple industries. I'm just checking to make sure I don't run you too far into lunch or to my next speaker. It's not always, again, intuitively obvious. Because we have multiple reactors in an array, you can support multiple industries simultaneously. That is not easy to do with a singular reactor. That's one differentiator when I compare ours to our competitors, is that having multiple smaller reactors in a single facility allows this to be easily managed. We've been working with a number of entities really focused on hydrogen, ammonia, and other products. We've done a number of studies, and I do want to point out that there is significant opportunity in Poland to be a hub, and this is beyond being an SMR hub, but being a hub for hydrogen production, ammonia production, and really, I heard the discussion of nitrogen. Oh, I wanted to discuss too, for certain countries we've been talking about, nitrogen for fertilizer, desalination, et cetera. To be able to do this from Poland to support the rest of Europe would be incredibly significant. Be the global leader. You may have seen recently that we announced some advancements with, and I want to make sure I get some of this right, so I'll go to some of my notes here. Advancements in our understanding of our own design and getting proven by industry to support heat generation, to support the steel industry, et cetera. I was going to say something here, I think. The biggest element that I wanted to raise here is to consider that a Voyager 12, which we always talk in megawatts electric, but it's something to consider that a Voyager 12 plant configuration can deliver 3 gigawatts thermal. That's an awful lot of heat to be able to deliver to industry. In advancing our technology, we assessed looking at what the capabilities of others were in order to be, just other technologies, not just SMRs, to be able to deliver energy for industry. And realize there's a number of limitations, and also there's a number of limitations in being able to actively support the use. So a large gigawatt-sized power plant, nuclear power plant, cannot be sited close to a point of use. So could you use that for district heating effectively and efficiently? Most likely not. Right? It's too big. You have to have an emergency planning zone that's much greater than, it really causes a lot of inefficiency for delivering the heat to the circuit, and it becomes really complicated, not cost effective, and really not effective. So the NuScale Power Plant, small emergency planning zone, meaning close to point of use, provides for easy use. We understood that the majority of industry, and this is based upon a lot of US effort because we got a lot of support from US Department of Energy, so I apologize that it's very US kind of based, but we recognize that 300 degrees C was a kind of a magic number for industry throughout the US and for other areas. So we targeted that, but we also realized that pretty economically, you can use a small amount of energy to raise the temperature and pressure of the steam coming out of a NuScale Power module to support the rest of the major industries listed here. So for district heating, desalination, most of petroleum refining and pulp and paper mills, which, by the way, pulp and paper mills are a large number of coal-fired power plants in the US. I used to support those in my old steam turbine days, and there's hundreds of those filtered throughout. As they age, they're looking, there's not, believe it or not, there's not less need for pulp and paper, surprisingly. We all think we're paperless, but we're really not, as I've got my papers up here. The energy is still necessary, and the energy needs keeps increasing. So how do you deliver that, and how do you ensure you can do it cost effectively to be able to remove those coal plants and make them work? And one of the things I did not prepare, I did not put a slide in here that I usually do, was to talk about how to reutilize the resources for a coal-fired power plant to be used in a NuScale power plant. It doesn't take that much effort to take a steam turbine maintenance person, a control room operator from a coal-fired power plant, and bring them up to the standards for a NuScale power plant. Granted, for an operator for a NuScale plant, we only need a small number of operators, a total of 9, for all shifts, all the time. You do need to have an engineering degree, et cetera. But during the process of developing the plant, from the point of doing your environmental impact and then construction, et cetera, you could be developing those resources. It's not overly difficult to do. It's always a question to us from those communities that say, okay, you want to close the coal plant, but what are you going to do for us? How are you going to help the community, and how are you going to help us progress? Not just bring a new technology in that leaves us all behind. That's something we've worked very hard on and diligently to be able to provide a relationship to bring that forward. That's something I think we all need to work together on as we talked about really elevating the sense of citizens to understand and appreciate nuclear, to really get them engaged, is to not say nuclear is for the elite, but to say nuclear is for all of us. I mentioned the steam compression efficiency and the 3 gigawatts for Voyager 12. There was something I really wanted to say here. Oh, I did mention the concept of steam compression and how it can efficiently bring up the pressure and temperature. I think that's all I really wanted to cover. I mentioned the carbon-free power project and the timing for that. I don't want to belabor this. I just did want to give you the context for later. And I did want to explain the value, and this is important, I think, the value of manufacturing the MPMs in a factory is that the entire plant gets constructed while those are being manufactured, which cuts down that entire cycle. This supports the theory of Poland being a hub for SMRs. This is just one example, and I know OSGE can point to others, and there's a number of other technologies, but also customers of ours that are looking to expand their sphere of influence, but are looking at Poland and Central Europe as a primary point of reference. Poland keeps moving at the pace you're moving and a little bit faster. You are the hub. You will continue to be the hub, and you'll be able to be the center point for global implementations for all SMRs. Keep up the pace, keep up the work, and let's leverage the supply chain to deliver. Feel free to come visit us in our and really take a good look at our plant simulator and understand how simple and easy it is to operate a NuScale plant. We're out in Corvallis in Oregon, and we're available. That's it. Oh, last thing. If they don't provide copies of the presentations, just contact me and I'll send you a copy, okay? Thank you.